Hi, my name is Johann Kruschwitz. I'm one of the developers of the GraphVar Toolbox, and today I'm going to speak about the community structure panel in GraphVar, which will enable you to make inferences about the community structure or the modular assignment of nodes across a group of individuals, or also compare this. So compare the community structure between two groups of individuals. In previous videos, I've shown you how to set up the general settings panel, so how to load in the individuals, but also how to perform network construction. And in this video, I'm going to speak about here the community structure, which is a panel which is initially hidden behind this little button, community structure. So if you press this, then you'll see a couple of new functions, which I'm going to talk about now in the next couple of minutes. For this, at the beginning, I'm going to toggle to a little presentation that is also entailed in the GraphVar download folder and that you should have on your computer when you've downloaded GraphVar. So what is this new feature? It can be used to obtain a group-based consensus of the graph decomposition, and essentially it's like a group ICA on graphs. So it enables you to obtain a community structure across a group of individuals, but also to compare the community structure, let's say, between two groups of individuals, and to find out whether the number of communities would be the same, the alignment of nodes to specific modules would be similar between those two groups, and so on and so forth. So how does this work? Well, it's called consensus community structure, and we perform this on two different levels. So GraphVar is doing this, so you don't have to care because, you have to care because you have to understand how this works if you want to report this in your paper, but you don't have to do this manually because GraphVar will take care of this for you. So in the individual level, we run multiple iterations of community detection algorithms, so you can choose either to apply the Louvain or the Newman modularity algorithm. And as you know from the previous presentation of mine about the introduction into graph network theory, those algorithms have a stochastic nature, so those are optimization algorithms. So the result of the affiliation vector, so which is basically telling you the assignment of nodes to the specific modules, can vary from run to run. So we run a couple of those and then aggregate those basically in a kind of co-classification matrix to then run a clustering algorithm on this co-classification. This is also called agreement matrix to determine a final clustering solution here in this end. And here, nodes frequently co-classified in the same module across multiple iterations of the algorithm will be assigned to the same module in the final solution. So this is basically a way of obtaining a relatively stable cluster solution, which can be seen as relatively valid because you aggregate now the results across multiple of those runs with the stochastic nature. And then this final assignment of nodes into the modules of each individual is then taken to the group level. And there, with the same logic, we create a consensus across the different single subject affiliation vectors. Specifically, those individual final consensus decompositions are summed across individuals to generate a sample-specific consistency matrix. And here, a high weight in elements of this matrix would indicate that two nodes were frequently classified in the same module across individuals. And therefore, a subsequent modular decomposition of this group level consistency matrix would ensure that nodes frequently co-classified together are likely to be assigned to the same module in the final solution. And there are two advantages of this two-step procedure, of this consensus procedure, because by aggregating results across single participant decompositions, this approach would also allow to derive, as I just said, a group level representation, which is relatively stable. But because we have all the individual information also in there, it allows characterizing inter-individual variability in network organization using two different metrics, which is the classification consistency and diversity, which in the end will enable you to draw inferences about the importance of specific brain regions with respect to their role in their functional module. For example, is it a hub, is it a local connectivity hub, within one module, or is it actually a region which may act as a bridge hub or a connection hub, connecting two different or various modules within the entire modular landscape of the final clustering solution. So how does this work? We now have possibilities to run this group community structure across all the subjects that you've loaded into GraphVar. So by simply hitting this button, it will run this consensus clustering across everybody that you've entered in here. But you can also perform group comparison, which in most of the cases will be the more interesting comparison. And then I'm going to run a sample analysis in a couple of minutes. You'll hit this button, two groups, then you'll be asked to define a grouping variable, and then you'll be asked to determine the number of permutations that should be run for group level inference. And this is similar to the non-parametric tests, basically by means of ID shuffling that we run for the GLM, because this enables you to get a significance value, let's say for Q, which is the quality function of the modular decomposition, by putting the real difference in Q between two groups in the permutation distribution of differences of randomized groups. And yeah, basically by determining then this delta in this random distribution of other deltas, right, from the other from the randomized groups, will enable you to determine the significance based on the percentile position in this respective distribution. So Q is always calculated. You do not have to make any selection on here. And then as I just said, Q is the measure for the optimal modular decomposition. So how modular is the graph? The higher Q is, the more modules you'll have in there. The lower Q is, the less modules you will have in there. And then there's another measure that you can use for making inferences whether modular organization would be different or similar across groups. So here we can use mutual information or variational information, and mutual information quantifies how much information is shared by the two partitions, and variational information is basically an opposed measure, tells you how the information varies between those graph partitions. And as you see here, this is, let's say now, again, the null model distribution that you'll get out for example, 1,000 or even 10,000 random ID shuffling across groups. And as you see here, it's basically opposed. So if the mutual information is not very high, so on this side of the distribution, then the variational information would be high between those groups. So you can use those, although they obviously also entail different concepts, basically as a checkup, because they should go in different directions. Then there is another thing that we can use, as I just said, the classification consistency and diversity to make inferences about the role of specific nodes with respect to each of those modules. And here, classification consistency is estimated by computing the within module strength, Z, of each node in the group level consistency matrix. And classification diversity is computed using the diversity coefficient H. And if you apply this in this context, then Z, so the classification consistency, would quantify the degree to which each region is classified in the same module across participants relative to other nodes in the same module. So this means now, this is written in red, that brain regions with a high Z value represent core components of their module and thus act as local connectivity hubs. And here, this is an example output that GraphVar will generate, which I'll show you in a couple of minutes, where Z is on the Y-axis. So this would be here, for example, a region with a really high Z value acting as a local connectivity hub. And the diversity coefficient H quantifies the variability of each region's modular assignment across participants. And thus, regions with a high H have a relatively equal probability of being classified into different modules across participants, right? So those connectivity is dispersed between modules from individual to individual. And these regions, and this is the important part, may therefore represent transitional nodes that facilitate information integration between modules. So this is what I said, bridge hubs or connector hubs, which facilitate information transfer throughout the modular landscape. Okay, now let's run an example analysis for you in GraphVar. So we are here in our group community structure panel, and now I want to do a comparison between two groups, and I want to calculate the classification consistency for making inferences about the specific role of nodes with respect to the modular alliance. So whether it would be a local connectivity hub or a hub that allows information transfer throughout the modular partition. Then I want to see whether the clustering solution, the final clustering solution for my group level consensus matrix would be different between the two groups, or whether they would indeed be the same. And I want to visualize those with BrainNet Viewer. Okay, I'm just applying this now on one threshold, but you could also apply all the computations now on, as usually done in GraphVar, multiple thresholds, or also on no threshold. So you don't have to threshold the connectivity matrix in any way for computations. But for our example, I'll put on the relative thresholding now with a sparsity of 0.46. Okay, but before I hit the two groups button here to start the analysis, there is something that is called the resolution parameter, the gamma. And I just show you this in my presentation again. Here, this resolution will tell you how fine-grained the resolution is to cluster the graph. So a gamma bigger than 1 will detect smaller modules, and a gamma lower than 1 but bigger than 0, so it cannot be smaller than 0, will detect larger modules. But gamma of 1 is basically the classic modularity, so the default in the brain connectivity script. Okay, so I'm opting now to choose to do my calculations on two groups. I'm giving the opportunity to do the Newman algorithm, which is a little bit older, or the Louvain algorithm. So this is the more widely used one. You may want to do a little bit reading what the difference is between those two. Then I'll be given the opportunity to select the variable which will define the two groups. So in this case, a categorical variable, two groups. So we haven't been able to, or I haven't had the opportunity to implement a version where you do calculations between three groups, so comparison directly with more than two groups. But for this case, we're just having sex here. Hit OK. Now it'll ask me to enter a specific number of permutations because, as I told you previously, we'll have to generate a null model distribution, and which we can use then to determine the non-parametric p-value of the true difference, for example, of Q, the quality index of the partitioning for the two groups, because this is then placed in the percentile position and is basically counted how many times group difference in the random groups was bigger or smaller, and then from there we can derive the p-value. Okay, now it's telling me that there are some negative weights in my respective sample already with a density of 0.46, but the Louvain algorithm can deal with negative weights in the current implementation as we have done it in GraphVar, so I'll just continue here. But depending on what your hypothesis about negative weights is, you may want to modify the weights, for example, by using the absolute weights over negative weights to 0. Okay, so this will run a while. It is already here 2 of 20 subjects, but I'll skip this to make it a little bit faster now. Okay, now we're nearly finished. 19 out of 20 subjects. Now 20 of 20. Now something should be popping up. Let's see what it is. Aha. Okay, so here you have the 3D embedding of the modular solution, the community structure, in one group, embedded by using BrainNet Viewer. This picture is already saved in your respective community folder in GraphVar in your current workspace. You see that there is already color coding for the different nodes and their respective community. The color coding is similar between the two groups. And here in one group, as I'm going to show you in a couple of minutes, we have 4 modules, and in the other one we have 5 modules. So let's look at this. Here, what came up in the female group. This is the community structure in the female group, and this is the community structure in the male group. So in the female group, we found 5 modules, which are those columns here, and the colors are represented in the first row. So red, yellow, green, light blue, and it's going to be the same here for the male group. And we see immediately there are only 4 groups, as we already saw here in the 3D plot of BrainNet Viewer, and those communities and the respective nodes are ordered here in those columns, and you see the sizes. So here the biggest community has 40 nodes, then comes 20, 16, and 14 regions, and respectively here in the male group, in the female group, there are 24 and 20 brain regions in the respective community, in the red and in the yellow one. And it could be the case, we'll have to find this out later, that the bigger community here of the males with the 40 is actually just split into 2 groups in the females, so 20 and 24. What we have here is that we have Q, this is the quality index for the female group, and the Q for the male group is 0.52. And now we want to see whether this quality index is different between the 2 groups. So we'll compute the difference between this. And this difference in Q of the real groups is now placed in the percentile position of the random group assignments. And now we chose to do 100. And you see here, it has been doing 100 permutations. And this is now the permutation distribution of the Qs in the random group, so the difference of Qs in random groups. And we see that our Q of the real groups is indeed at the really high percentile position here of the null model distribution. So it's actually significant. So we can say that the 2 groups here, females and males, are significantly different with respect to the quality measure of how modular their partitions are organized. Okay, now let's have a look at whether the assignment of nodes to those clusters would also be significantly different between the groups. So this is again our Q, so this is different. So females have 1 partition more, so 1 community more than the males. But, and here we have the mutual information and the variation information, it's both not significant. So we see that although there is 1 module more across the modules, the assignment of brain regions to this respective communities seems to be relatively similar between the 2 groups. So the mutual information is relatively high, so they're sharing a lot of information, and the opposed measure is the variation information. This is relatively low, so it's not that they do not share or that they do not have so much unshared variance. And if we look again here, this is the difference of the variational information between the actual groups, and based on this position in the null distribution, on this percentile position, it is not significant, and the same counts for the mutual information. So what else can we look at? We can now look at the plots of classification consistency versus classification diversity here for the females and here for the males. And at first glance, it doesn't seem, just eyeballing, so increasingly different, the distribution. So it's also this linear trend. But this is what you'll observe also most of the time, that's the linear trend, because if a region has a really high classification consistency, then it's a regional hub, and then it is never basically a region with a high classification diversity, which would then be a transitional hub throughout the modular landscape. Okay, here the dots seem a little bit less, the brain regions, but it can be that the Z and the H values for some regions are exactly the same or nearly the same, and then MATLAB just plotting them or grouping them accordingly. So let me show you a different example of somebody who did the same analysis. So this was published in the Journal of Neuroscience already in 2012, so by Alex Fornito, and we basically
copied most of the analysis steps that are implemented in this paper, in this group community detection module. And here they also have those plots with the classification consistency and diversity. It's exactly the same as with us. But here, this would be something striking. For example, they show that if they compare two groups, one has only 2 modules, the other one, they have 3 modules. And the third module, what you see here in this respective plot, is characterized by correspondingly high classification diversity, and medium are also reaching to a high classification consistency. So it could be that these are transitional nodes that then facilitate information transfer throughout the landscape, but are also really important, especially this one, to enable information transfer within the same module. And they relate this then to different task sets and so on. So this is a really nice paper, and we've basically implemented what they've done here in GraphVar. So, but here, if we now look at this, we do not see that there is this striking difference. So, but what would be interesting for you is to see if there are differences in the values of the classification consistency or classification diversity between the two groups. And this is what GraphVar already plots out at the end of the permutation. So for each single node, the Z and the H value, it is generating for the difference of this value among the groups, a permutation distribution, and placing the real value in there. And these are now, according to 0.05, an alpha of 0.05, the ones that are significant. I'm going to show you in a minute where you can find those files in GraphVar to get access to those values and yeah, to use them further for your analyses. But let's first have a look again at those plots. Where are they? Here. Now, it is really important to say that the communities are not necessarily the same if they have the same color, right? Here, the red community must not necessarily be the red community in here. It is just ordered red because we always give red to the biggest community in each of the groups, right? So here red is the one with the 24, here yellow is the one with the 20 nodes, and here red is the one, again, with the biggest one, and yellow is the one with the 20 nodes. But it must not mean that the yellow one is equal among those among those groups. This is a little bit difficult to know and to judge because it's a heuristic algorithm, and so it makes comparison a little bit difficult, but we can do this based on the overlap of nodes with respect to the module. And I'm going to show you this here in this little presentation in the output file. So here is this is saved in the output folder GraphVars in your sample in your respective own workspace. And here we run a script which will compute the overlap of nodes in the modules seen from the position of group 1 to group 2, and overlap of nodes in the modules from group 2 to group 1. Right, you always have to look from two sides to actually get a grasp on what this means. So group 1 could have module A, and module A has an overlap of 90% with module A in group 2. But if you look at the other way around, module A in group 2 could only have, let's say, a 20% overlap with module A in group 1, which tells you that module A in group 2 is probably a real big module and also could be then shared either by many other modules in group 1 or just another module in this respective group. Okay.
So let's have a look at an example of what I mean by this explanation. Therefore, I'm going to my MATLAB window and to my respective workspace, the interim workspace. Here are a couple of variables in the GraphVars, which I'm going to explain you in a minute what all this is. But right now we're talking about the overlap between the groups to find out which module corresponds actually to which other module in the other group. And here are two files, modularity overlap percent from the females, from the perspective of the females to the males, and here and beneath from the perspective of the males to the females. So let's have a look how this looks like from the females to the males. So we know that in the females we have five communities found with our calculations. So here the rows are the ones that we're interested in, and everything across the columns adds up to 100%. So we see that module 1 or community 1 in the females overlaps to 100% with module 1 in the males. And we see here that module 2 is basically shared between two modules in the male group, namely to 40% with module 1 and to 60% with module 2. But here, for example, module 4 corresponds to 100% to module 3 in the male group, and the nodes of module 5 in the female group correspond to 100% to the nodes in module 4 in the male group. Now let's look from the other side, because it's always, as I said, important to take both sides. And here now we have the view from the males to the females, and here the rows add up to 100%. So those are the four modules we're interested in, we're looking from now. And we see that the module 1, which we know is the big module, we can just toggle back here. Module 1 in the males is the really big one with 40 nodes. This is distributed among the modules of the females to 60% in module 1, to 20% in module 2, 20 in module 3, right? So this big module is actually distributed among the three modules here. And what I meant specifically, that we now know that module 1 has in the male group has to be bigger than module 1 in the female group. It's because if we just look here from the female perspective, their module 1 is totally incorporated into module 1 from the males, but if we look from their side, only 60% of module 1 is actually also similar to module 1 in the females. So we know that 40% must be distributed among the other modules. So we know that the module 1 in the males must be bigger. So this is what I meant with my explanation just a couple of minutes ago, when I said, hey, we have to look from two groups here on this side. Okay, so what else can we then see? If we now look at our plots again, here, the classification consistency and diversity plots, it would then be interesting to know, okay, so I showed you how you can figure out which module would correspond to which module, more or less, with this percent overlap table. And now it would be nice to know, for example, which region, if you're interested in this particular region here, this green one, with an X of 0.76, this would be the diversity, and the consistency of minus 0.16, which region this is. Therefore, I haven't had time to actually program that you see the actual name of the region here. But for this, you just go then in the group community folder. This would be, where is it? Yeah, here in Graph, not GraphVars, but in the respective workspace, group community. Just go down here. You see this this bunch of files, which is explained in here in this little presentation. And then you would just have to open the classification consistency file, right? This would be for your respective group. Now we were interested in looking here at the females to find out what node this actually is. So we'd go in here in the first group. This would be then the female group. Look at this file, the z-score, and can plot this. This is a vector, one value per node, and we can plot this accordingly then with the classification diversity, which is also one value per node. So by plotting those vectors, you can really fast then figure out which node actually belongs to this, because you can pair X and Y with those vectors that we put out for you here. Okay, let's just go one step back to see what else is actually saved in our file. So from those distributions here, this one, the permutation distribution of variation information, the permutation of Q, and the permutation of mutual information, we always give you the true difference between the groups, and we always give you the non-parametric p-value. And the files where those values are stored, you find in the GraphVars in your respective workspace in the subfolder GraphVars. The actual mutual information, actual variational information, so what we compute as a measure of difference between the groups, is stored in this file, actual MI, actual variation information. Then the difference in Z and the difference in H. So this is one value per node, respectively, right? Because I showed you here that we have this classification consistency, one value per node, and diversity, also one value per node. There we compute the difference between the two groups. So you would have the difference, respectively, for each of the nodes in those files. And we also have the actual difference in Q between the groups. So this would then just be one value in this respective file. Based on those, we can determine the p-value, because here we have permutation distribution, or our permutations of the groups for each of the values. And here then we generate the distribution, which is already sorted, right? What is the mutual information of any of the random groups, let's say 1000 or 100 repetitions, as we've done right now, ordered from smallest to highest mutual information for the variation information similarly, and also for the distribution for Z and for H and also for Q. And then, as I explained to you also previously and also in the videos, we just put this difference of the true, or this difference value of the true of the true group assignments in the respective distribution of those permuted groups, which you find here, the original permutation. And then based on the percentile position, we can determine the p-value, which you find here at the bottom, for H, 1 per region, and Z also 1 per region. And yeah, it's just 1 for the variation information, for the mutual information. And here I can come back to what GraphVar shows you when it's finished with its computation. So here the p-value for H, p-value for Z, and those are the ones which are actually put out from GraphVar again here. So the index means the index of the brain region that you've used. Let's say I have 116 brain regions, then I know the 11th brain region in my case, and you have to figure out what this is in your case, would be significantly different according to the p-value for the Z here that we determine here based on placing the actual Z in the distribution of this respective node. Okay, now let's go one step further to the group level statistics now. So in the other than the files I showed you previously with the overlap, there are different files generated in here. So we've spoken about the diversity and the consistency, but we also have a file of the respective modularity index Q for each of the group. You can access this one here. But most importantly, I told you that it's basically a two-step procedure. So we have the individual level computations, which are then taken to the second level computations. And the second level computations basically are based then on this group level consistency matrix. And the group level consistency matrix, on this matrix, then the clustering algorithm, Louvain or Newman respectively, is run, right, to determine the final cluster solution. And the final cluster solution is here, this affiliation vector, so the assignment of nodes to the final modules. So this is a vector of numbers. Here, let's say for our females, we had 5 modules, so it will be a vector comprised out of 1, 2, 3, 4, 5 of those numbers, respectively assigned to the nodes, right? And the nodes would be the rows in your respective vector. And then we also give you something out, which are the binarized affiliation vectors. So you'll have, and this I show here on the last slide, binarized affiliation vectors would be for, let's say those could be the males we found out. We have 4 modules, and here it is coded with 0 or 1 with the respective node, and here the nodes are the rows. would belong to module 1, 2, 3, or 4. So you see it's unique. If it's 1 in module 2, then it must be 0 in the other ones. And you can use this binarized affiliation vector for including in your, then in a subsequent step in your brain regions file. If, for example, you just do then analysis with the male group and just want to do analysis or compute specific graph measures, so basically subnetwork analyses only in a respective module. So then if you're just interested in module 4, you can take this binarized affiliation vector, put it in the first column in the brain regions file, and automatically in GraphVar, those will be highlighted. So you don't have to do this manually. Okay. I've spoken about the two-step procedure. So we have the first level and the second level. For the second level, the affiliation, the group level consistency matrix, I've shown you where you can find this, but you can also find it for the first level computations. So here, this would be the agreement matrix. So the subject level consistency matrix, basically, after all the computations, which is generated for one subject, on which then the final modular assignment for this subject is determined by running the modularity algorithm again. And then here at the bottom, you see this is the subject-specific affiliation vector that shows us the final first level subject, and this is 1 per subject modular solution. And those, just to explain it again, those are carried over to the second level, and the group level consistency matrices are then built upon this, on which then the final group affiliation vector is generated by running this algorithm again. Okay, so this is more or less everything that you can do with our group community panel. So to sum it up, you can do analysis across all subjects, compare different characteristics between two groups, there specifically the quality index of Q, but also look at the classification consistency and diversity. You can then determine based on those plots if there are, let's say, specific nodes that are really important as being part of a local connectivity hub, so in the respective module, or rather ones that would facilitate information transfer by means of a high classification diversity. So those measures are computed on final consistency matrices. But you can also look whether the groups, the two groups, are different by means of mutual information or variational information, basically kind of cluster distance, whether the clustering would be similar between the two groups. We can visualize everything with BrainNet Viewer, and to find out which regions or which modules correspond to which module here across the group. I told you that the colors are not do not indicate that this is really the same module, but then you can use our percentage overlap analysis, basically identifying the backbone structure, which nodes are shared among which modules, and then determine, as I showed you, hey, module 3 in the female group corresponds to module 4 in the male group. So this is basically how you can start off, and we provide you with all the files that you can later on use for your own further analysis. So I have to apologize already at this in this video that as you see, there are so many different windows that are opening, so we haven't had time to write a really convenient results viewer, but I think this new results viewer for the community analysis will be up, I hope, in a couple of releases when we have some time to sit down actually to do this. Okay, thanks for watching. Bye-bye.